Hi, welcome back. Today we're looking at 4.2, which has to do with the mean value theorem. I figured if we're going to talk about the mean value theorem, we may as well refresh on what is called the intermediate value theorem once we get done with the mean value theorem, because they are very closely related. So the mean value theorem, what it says in mathese language, if fx is continuous, so that's the blue line I have here is fx, for interval a to b, here's my a, here's my b, and you'll notice that we're including a and b, and differentiable for interval a to b, not including a and b. We'll kind of talk about that in a second. Then at minimum, there exists one point on f of x that has a tangent line that is parallel with the interval of the function's secant line. Well, the secant line is like an approximation of the tangent line. Tangent line is instantaneous, secant line. What we've done is we've taken this function over the interval, and the secant line is linear, and it goes from x is a to x is b, and from f of a to f of b. And so the slope of the secant line could be written, let's write it like this. So the slope of the secant line, we'll call it M, SEC, is going to equal rise over run, right? So rise is from FA to FB, so we've got FB minus FA, and we're dividing it by the change in x. So we did the change in y. Now the change in x is going to be b minus a. So this is the slope of the secant line. And what this is telling us is that this is the slope of just this line between these 2 points, the starting and ending point of our f of x. And what this theorem is saying is that on the true graph f of x, which in this case is a little more curvy, there must be at minimum one point on the graph. Typically we call that point C. Let's focus in on this one. We'll call this x equals c, because this is one of the points where the secant line that we've created and drawn, this is one of the points on f of x where the instantaneous slope at that point c is actually parallel to the secant line. And in our example, we actually have 2 points that are parallel, where their instantaneous slopes are parallel with the secant line. But all the all the mean value theorem tells us is that there is a minimum one if the function is continuous. And we can kind of see why it needs to be continuous. For example, if my graph could go like this to here, and then disappear here and reappear here, like a piecewise function, there would be no mean value theorem, because with the discontinuity, there's no guarantee that you're going to have a nice smooth curve. And then likewise, it must be differentiable, because if you could do a spiky, like instead of a curve, which means it's differentiable, if you could go up to a spike and instantly change directions at some really large angle, then you may as well be able to avoid any points where the tangent of those points are parallel to the function secant line. So those are both important. The reason why continuity must be on interval AB including AB is because, like for example, let's say that there was a hole in the graph and then it filled in up here. Or if there was a hole in the graph here and then it filled in up there. Well, if you can avoid continuity on the endpoints, you can also find a clever way to avoid the mean value theorem. Whereas with derivatives, we know that this point right here and this point right here on the end of our intervals can't have a derivative at that point if we are limited there, because you'll notice that for a derivative to exist, we need to have a right-handed and a left-handed limit agree. And it's pretty clear that there's no left-handed limit for a function that ends at this point, and there's no right-handed limit for a function that ends at this point. So for our differentiability, our ability to take a derivative, we don't need to include a and b, but we do need the whole interval a and b to be differentiable not including a and b. And so this is the slope of our secant line. And also, what else we're going to call it is we're going to call it f prime of c. And the reason why is because if we take our f of x, right, this curvy function, f of x, and we take f prime of x, then we have created a function that will tell us the instantaneous slope at any point on our f of x graph. So you give me the x value, I'll give you the slope. And as we've talked through, there must be a point C, at least one of them, where the slope of the instantaneous point on that graph is parallel to the slope of the secant line. So if the slope of the secant line, m secant, is equal to fb minus fa over b minus a, that's this secant line. And if our point x equals c has a parallel slope to that secant line, then we can say that m secant is equal to the derivative of f of x when we plug in c, because that's going to give us our slope. And so this is the mean value theorem from a conceptual point of view. I'm going to go ahead and do the intermediate value theorem real quick, because to me it's striking. It's very similar. And so with the intermediate value theorem, instead of talking about slopes and derivatives, we're actually talking about just plain old functions with no derivatives included. So let me go ahead and write this up here. And this is an algebra theorem, the intermediate value theorem. But it's easy to forget. And after I show it to you, you may say, well, this is so obvious, why even bother? And that may be the case, but I saw a striking similarity between these two theorems. So likewise, we have an xy coordinate. And what the intermediate value theorem states is, like, for example, if we have a continuous function, so let's say it looks like this, do something similar to the last time, across some interval x equals a to x equals b, then what we're going to say is that at x equals a, if we plugged in x equals a into the function, we would get f of a as an output. So the y value for this ordered pair is f of a, whereas the y value for this ordered pair is f of b, because we're plugging in b and we're getting an output. So this is f of b. And what we are saying here is that, let's say that there is some, let's say that we're moving across this line, and we're interested, do we ever cross this point C, we'll call it. And so what the intermediate value theorem states is that if f of x is continuous along this interval AB, and we start, and our highest value is FB, and our lowest value is FA for outputs, what we are going to say is that any value C that exists between FB and FA, so any value C that exists between FB and FA must exist somewhere on this graph. And we can find that point right here. And so this is really useful for, like, example, if you're solving for zeros on a polynomial. If you're looking at a smooth and continuous polynomial, and let's say that you have just sort of a parabola. If you know that there exists a point up here that is positive in the x and positive in the y, and then you also know of another point down here that you plugged in and found that is positive in the x and negative in the y, and this function is continuous, you know it must have crossed the y equals 0 line. And we can see that to be true, only if the function is continuous. So this one is a little more obvious, but it definitely has some parallels to the mean value theorem, and I just wanted to go ahead and show it. The next video we're going to do a practice problem with the mean value theorem. And so I'll see you then.